Welcome back to the course of Applied Elasticity. In this lecture, we are going to continue our discussion on the bending of beam problems. So, we had started our discussion on bending of beam, where beam is an one dimensional continuum where the length of the element or the continuum is much larger as compared to other two dimensions, and this undergoes bending when it is subjected to either bending moment or any kind of transverse shear loading. So, we are considering the bending of beam problem under different types of loading. Till now we had solved three different problems. The first one is bending of a cantilever beam subjected to pure bending, then bending of a cantilever beam subjected to the concentrated shear load at the free end, and third one was bending of a simple supported beam subjected to uniformly distributed load over the entire span. Now, in today's lecture we are going to consider a fourth problem where the beam is subjected to linearly varying distributed load. So, difference between the previous one and the present one is, for the previous problem third case, the load acting was having constant intensity over the entire span of the beam, whereas in this one the intensity of the load is varying linearly. So, at one end it is 0, at another end it is maximum. So, this is the distribution W, this was W which is constant, force per unit length was constant for UDL, whereas linearly varying distributed load, this W is a function of x and that is linear function. Okay. So, let us start it. We are going to consider a cantilever beam fixed at one end and free at another end, subjected to linearly varying distributed load on the top face. So, let us consider this beam where the left edge is fixed. So, origin is somewhere here 0, 0, 0. Now, length is taken to be L, total depth is taken to be twice d. So, y is varying between minus d to plus d, x is varying between 0 to L. X equals to 0 refers to the free edge. So, this edge is x equals to 0, whereas x equals to L refers to the fixed edge, that is on the left hand side. Now, coming to the loading, you can see this Fx is the linearly varying distributed load intensity, which is equals to P x by L. So, at x equals to 0, that is at the right hand side at the free edge, if you put x equals to 0, F 0 will be 0. Thus, at the right hand side at this particular point x equals to 0, the value of the load intensity goes to 0. With x equals to L for the left edge, that is the cantilever or the fixed edge, with x equals to L, Fx will go to PL by L or a constant P. Thus, this P is there, which is the highest value, the maximum load intensity occurring for this linearly varying load at the left edge or at the built in edge. So, L is length, B is width, 2d is overall depth or thickness, P is the maximum intensity of the linearly varying distributed transverse shear load, which occurs, this P occurs at the cantilever or built in end or at the left edge. Now, coming to the boundary conditions. So, as there is no axial force present in the problem, we are having integral b sigma x x dy equals to 0, integral is from minus d to plus d. Note that total depth is 2d. So, range of y is from minus d to plus d. So, y is varying in this range, not d by 2, minus d by 2 to plus d by 2, total depth is 2d here and x is varying between 0 to L. Now, coming to the next boundary condition, that is bending moment at any x. So, if you are considering any x, let us say somewhere here. Now, what would be the bending moment? So, bending moment left hand side expression m equals to b sigma x x y dy integral from minus d to plus d. Now, right hand side is the expression of bending moment due to this linearly varying load intensity f x. Now, that is obtained as p x cube by 6 L. So, how can that be obtained? If you are considering this particular section, the total load acting within that span is this much triangular load is acting. So, what is the total area within this? So, here this height is equals to p x by L, and this bottom length, base length is x. So, total area will be half of p x by L times x. So, p x square by 2 L. So, the total shear load acting at this section, if you cut the section here at any x from left end, you will be getting the shear load to be equals to p x square by 2 L, which is the total downward load coming due to that portion of the triangle, that portion of the linearly varying load. Now, coming to moment, at this section some moment will also be there mx, which is equals to basically moment of this linearly varying load about this particular surface. That can be obtained by choosing the centroid. So, if you consider this triangle, the centroid of the triangle is somewhere here, through which this load p x square by 2 L is passing, and the distance of this centroid should be at a distance of x by 3 from the base of the triangle. So, this is well known from geometry. Now, the moment of this uniformly distributed load about this particular section would be x by 3 times p x square by 2 L, which is p x cube by 6 L. That is what is written here. So, moment at any section x would be p x cube by 6 L, and that is equals to integral minus d to plus d b sigma x x y dy. Coming to the vertical shear force. So, vertical shear force, as I told, at any section is this p x square by 2 L. Now, if you are considering the fixed edge, the left hand side edge, vertical shear force at that particular edge should be equals to p x square by 2 L at x equals to L, because x equals to L refers to the fixed edge, the left hand side face. So, putting x equals to L there, it would be p L by 2. So, net vertical force on the left hand side, that would be equals to integral of b tau x y dy from minus d to plus d, and it should be p L by 2, and this is positive. Note that this should be positive. Why? Considering our element positive x being on this side, we should have tau x y to be upward on that face. Here x axis is towards left positive. So, tau x y should be positive there, and this shear force is upward. So, this is the net upward shear force p x square by 2 L at x equals to L, which is having same direction as tau x y for the positive x plane. Thus, integral b tau x y dy from minus d to plus d should be equals to p L by 2. This is the third boundary condition. Now, coming to the next one, this is along the bottom face sigma y y and tau x y both should be equals to 0. So, this bottom face is defined by y equals to minus d, and this is free of any kind of normal or shear traction. So, both sigma y y and tau x y should be 0 for the bottom face, whereas for the top face, that is defined by y equals to plus d. For that, tau x y is 0, but sigma y y, the normal traction is non-zero. Normal is acting like this for the top face sigma y y, and that is non-zero because of this P x by L. Now, once again P x by L is the intensity, maximum load intensity for this linearly varying load. So, this is defined per unit length. Hence, if you divide this by B, we will be getting the equivalent stress quantity, the force per unit area. So, sigma y y for the top plane y equals to plus d for any value of x would be equals to minus P x by B L. Why minus? Because P x by L is acting downward, whereas sigma y y for the top plane is acting upward. So, that is why a minus sign is coming, and tau x y is 0 for the top plane because no shear fraction is there on the top face. Now, coming to the free end face, that is this face, right hand side face, that is defined by x equals to 0. Sigma x x, that is normal stress on the right hand side free edge, is 0. Tau x y, that is shear traction on the right hand side face, is 0 because that is free of any kind of external tractions. So, these are the 6 boundary conditions which our solution should satisfy. Now, the choice of stress function here is something like this. If you recall the previous 2 solutions, when we were solving for the bending of beam problem with a single transverse shear loading acting at a single section, for that we were taking the polynomial up to 4th degree. Then when we are going for the uniformly distributed loading over the entire span, we have to take a polynomial up to 5th degree. Order increased or degree of the polynomial increased by 1 when we are increasing the order of the load. So, here we are going for uniformly distributed load to linearly varying load. So, basically the expression of the load, if you write mathematically, we are increasing the order of the load, means if you integrate the previous load, we are that constant UDL load, we will be getting a linearly varying expression. So, with integrating the previous load, we are getting this linearly varying load. Thus, order of the polynomial required in the stress function should also increase by 1. So, here the highest order required to be considered in the polynomial is 6. So, solution should be combination of 2nd, 3rd, 4th, 5th and 6th degree polynomial. So, there will be a long expression of phi, which is general expression of superposition of 2nd to 6th order or 6th degree polynomial. Many of the constant would be there. Then if you start solving it after putting the boundary condition, a huge set of constants will set to 0, as you had observed in last 2 problems. Now, here I am only considering a solution with these 6 terms which are going to result non-zero constants. You can start with a general solution with let us say some 20 or 25 terms, and then after following a similar procedure as discussed in 2 previous lectures, you will end up with many of the constant to be 0 and only this 6 non-zero constant will be left. So, I am directly starting with this solution for reducing the complexity or reducing the computational complexity rather. So, only non-zero terms present in phi is a1 x y plus a2 x cube plus a3 x cube y plus a4 x y cube plus a5 times 5 x cube y cube minus 3 x y to the power 5. You can note that these are the 6th order terms. Now, this must satisfy the biharmonic equation. Now, as I had already told, I had set the 0 constants out, and thus this particular choice of phi satisfies the biharmonic equation automatically. So, whatever conditions are required to be imposed to satisfy del 4 phi equals to 0, that I have already incorporated, and thus this chosen form of phi stress function satisfies the biharmonic equation directly. Now, from this we can obtain the stress component sigma x x as del 2 phi del y 2, sigma y y as del 2 phi del x 2 and tau x y as minus del 2 phi del x del y as this. So, these would be the 3 equations for the 3 stress components, in plane stress components for the present problem with these chosen form of phi. Now, we need to see whether this satisfies all the boundary conditions or not. If yes, what should be the values of these constants A1 to A5, so that we can obtain the overall stress distribution for the bending of a cantilever beam subjected to uniformly varying load. Now, starting from the boundary condition 4 and 5, that is shear traction for top and bottom face are 0, tau xy is 0 for y equals to plus minus d. This is the expression of tau xy. If you replace y with plus minus d and x remains as x, it should be satisfied for all values of x. So, we will be getting this equation. Here you can see there are 3 terms, these 3 which are constant terms independent of x, whereas 2 terms are there, this one and this one, which are dependent on x square. So, this equation would be 0 only if the constant term and the coefficient of x square are set to 0 independently. Thus, minus a1 minus 3 a4 d square plus 15 a5 d4 equals to 0, minus sign is cancelled from all the terms and we are getting the first equation, that is setting the constant term to 0 and setting the coefficient of x square to 0, we will get this second equation 3 a3 plus 45 a5 d square is equals to 0. So, from here we got a relation between a3 and a5 as a3 equals to minus 15 a5 d square. Going to the remaining part of boundary condition 4, sigma yy at y equals to minus d is 0, bottom face is free of any kind of normal traction. Putting the expression of sigma yy, this expression with y equals to minus d, we will be getting this equation, this entire term 6 a2 minus 6 a3 d minus 30 a5 d cube multiplied with x equals to 0. This can be satisfied for all values of x if this coefficient of x is equals to 0. Now, we know a3 and a5 are already related. So, here this a3 and a5 relation is substituted and a2 is written in terms of a5 as minus 10 a5 d cube is equals to a2. Now, going back to the remaining part of boundary condition 5, that is normal traction on the top face, sigma yy for y equals to plus d is minus px by bl due to linearly varying load. So, once again in the expression of sigma yy substituting y with plus d, we would be getting this equation 6 a2 plus 6 a3 d plus 30 a5 d cube times x is minus px by b. Here we can cancel x from the both sides, a3 and a2 both are known in terms of a5. So, we can replace them, then this equation would give us the expression of a5 directly in terms of p as a5 equals to p divided by 120 lb d cube. So, we got one of the constant. Now, substituting this a5 back here, we would be getting a2 to be minus p by 12 bl and substituting this a5 back here, we will be getting a3 to be minus p by 8 lbd. So, 3 values, 3 constant we had obtained a2, a3 and a5. Now, after this we are going to check the remaining boundary conditions on sigma xx. So, sigma xx is written here which we had obtained, and then the constant a5 in sigma xx is already obtained as p by 120 lbd cube. a4 is the remaining constant to be evaluated. Now, using the first boundary condition, that is the condition of 0 axial force, integral b sigma xx dy from minus d to plus d equals to 0, replacing this form of sigma xx in this particular integral equation, we will be getting this term. Now, here this equation is automatically satisfied because sigma xx is an odd function of y. So, you can see only y term or y cube terms are present in the expression of this sigma xx, and y integral is from minus d to plus d. Thus, for the sigma xx being an odd function of y, this equation will be automatically satisfied and will go to 0. So, this equation is satisfied, boundary condition 1 is satisfied, and we cannot find A4 using this particular condition. Now, let us proceed to the second boundary condition, which is the moment balance equation. So, moment at any particular cross section is written as p x cube by 6L, and in terms of sigma xx, that is integral b y sigma xx dy from minus d to plus d. Now, here if I am replacing these form of sigma in this particular equation, then it would be something like this. Now, integrating the left hand side with respect to y from minus d to plus d, we will be getting these two set of terms. The first term you can see that contains x cube, some constant 20 a5 bd cube times x cube, and second term is containing x, which is having a coefficient 4 a4 bd cube minus 24 a5 bd to the power 5. Now, comparing the coefficient of x and x cube on both the sides, on the right hand side x cube coefficient is p by 6L, that should be equals to the x cube coefficient on the left hand side. Similarly, as there is no term on the right hand side with x, the left hand side coefficient of x should be 0. So, we will be getting these two conditions, from which from the first one a5 can be obtained as p divided by 120 L b d cube, and using that a5 here in the second condition, we will be getting a4 to be p divided by 20 L b d. So, we are getting both the constants a4 and a5 associated with sigma xx here. Now, if you check, we had already obtained a5 from one of the previous boundary condition, and comparing them you can verify that this a5 form is same from this boundary condition 2 and obtained from the previous boundary condition. So, as we are getting the same constant from different boundary condition, means the chosen stress field is valid. This is compatible with all the boundary conditions. Now, we are only left with a single unknown, that is I guess a1. Now, using the expression of tau xy, this is tau xy where apart from a1, rest of the constant a3, a4, a5 are known. Replacing that in the expression of tau xy, we would be getting tau xy to be this: a1 first term is unknown minus a1, rest 4 terms are known in terms of x and y function. Now, the remaining boundary conditions we need to satisfy. B tau xy at x equals to L integrated over minus d to plus d is equals to PL by 2, that is at the cantilever end total shear force, upward force is PL by 2. Now, putting this tau xy here with x equals to L, if you integrate it and equate that to PL by 2, the left hand side is having only one unknown constant a1. So, solving this, we can get a1 to be minus PD by 40 BL. So, by using the third boundary condition, that is balance of the vertical shear force at the cantilever end, net y axis force balance will give us this last remaining constant a1 as minus PD by 40 BL. Now, all the constants are known. So, substituting this a1 back here, we will be getting the complete expression of tau xy. So, I have written the expression of sigma xx, tau xy and all the constants whatever are involved there. Now, the remaining boundary condition 7 was sigma xx and tau xy to be 0 at x equals to 0, that is at the free edge. The free edge is free from any normal traction, and that is also free from any shear traction on the right hand side, that is for this free edge of the cantilever beam, this particular edge. This edge is x equals to 0 edge. So, these should be having sigma xx 0, tau xy 0. Now, if you put x equals to 0 in the sigma xx expression, it will directly go to 0. So, this equation is automatically satisfied. Coming to tau xy at x equals to 0, here in x equals to 0, in tau xy, if you replace x equals to 0, this term and this term would cancel, but 3 other terms would remain where one term is constant, one term is function of y square, another term is function of y 4, and this a1, a4, a5 are already obtained as non-zero constants. So, for all values of y, it is impossible to force tau xy to be 0. It is not possible to satisfy this particular equation. So, for all values of y, thus at the free edge, one of the surface traction, that is shear traction boundary condition on the right face, right free face is not getting satisfied at x equals to 0. And moving to the last remaining boundary condition, no, I think all the boundary conditions are now satisfied. Now, we are replacing this a1, a2, a3, a4, a5, all 5 constants which we had obtained in terms of the load intensity P. If I replace all of them in sigma xx, sigma yy and tau xy, the expressions of the stress field would be obtained like this. Sigma xx is 3 p xy by 10 lbd plus p xy by 4 lbd cube times x square minus 2 y square. Here you can see we are having the cubic order variation of sigma xx in terms of x. You can see one x is present here which will be multiplied with this x square. So, the sigma xx is proportional to x cube. From the first term it is proportional to x. It is also proportional to y for first term, and here it is proportional to y cube from this term. So, here we cannot just say sigma xx is my by I, that particular assumption is not valid. Here sigma xx is proportional to y cube as well for this particular type of linearly varying load. Then similarly, substituting the constant in sigma yy and then in tau xy, you will be getting this equation. So, in total these 3 expressions of sigma xx, sigma yy and tau xy give us the stress field, stress components generated for the cantilever beam subjected to linearly varying load. And note that we are able to satisfy all the boundary conditions except one, that is on the free edge, the tau xy was not, we were not able to force that to 0. Apart from all rest of the conditions are satisfied. Now, following the Saint-Venant's principle, these results are applicable for the region apart from the 2 edges x equals to 0 and x equals to L. So, in total in this lecture we had discussed about the bending stresses for a cantilever beam subjected to linearly varying distributed load. Thank you.